Talk today, space weather and the origin of life. Kind of broad concepts, and what I'm going to do is I'm going to break them down throughout this talk. So just a quick shout out to all the co-authors on the bottom. I think Vlad's here, so one of the co-authors is watching, and then all of our institutions. So what this project is, it's looking at space weather, so stellar activity around active young stars and how it could impact the origin of life on young planets, specifically the Earth. So since this is an exoplanet talk, people are probably most familiar with the concept of space weather or these high solar particle events. So what I'm going to do is I'm going to start by talking about the origin of life, just kind of give everyone maybe the same baseline where we currently stand on origin of life theories and environments for the origin of life. Then I'll jump into what space weather is and how I'm using that term and how it impacts the environments for the origin of life on these young planets. And then at the very end, since this is an exoplanet talk, we can generalize this to other planetary environments than the Earth and what that could potentially mean. All right. So origin of life, when did it occur on Earth? We're using Earth as a starting point just because we know there's life here, and then we can speculate elsewhere afterward. So here's Earth throughout time. Definitive evidence for the origin of life, we have it placed at least at about 3.8 billion years in the past. I think if you can see my cursor, the most definitive evidence is probably these stromatolites, which are these microbial mats from that period. And then we also have slightly less definitive evidence of potentially fossilized bacterium. And then if we want to get more speculative about when origin of life occurred, there's some speculative evidence going back to like 4.1 billion years ago. And these are looking at, carbon inclusions in these zircons from Jack Hills. And just based on how depleted the carbon is, they make the argument that it is biogenic in origin. And that's much more speculative than actual like fossilized remains of life like stromatolites, but it does give us an idea of when life did originate, and it's somewhere at this Hadean-Archean boundary. So we know there's life in the Hadean. We don't know when it started, but it gives us a starting point for what the environment may have looked like, both on the planet and also the host star. So where did life originate? That's kind of been a big debate in the literature for the last several decades. One of the popular theories has been hydrothermal environments. Hydrothermal environments do have a lot of pros going for them. Some of it is just the strong redox gradient that naturally occurs at these environments, and I'll talk about what that redox gradient is. And you just get a very reduced environment, which could be beneficial for the origin of life. And then the second one is surface environments. Surface environments for the origin of life used to be more popular. And the idea behind that was people thought the Hadean Earth had a very, very reduced atmosphere, so ammonia, methane rich. And that has been beneficial for producing prebiotic molecules historically. So going all the way back to the Miller-Urey experiments, where they had these very reduced gaseous mixtures, and they would do spark discharge experiments. And, they would see how many prebiotic molecules they could produce. However, with photochemical modeling evolving, very reduced atmospheres were likely very transient. They may have occurred in the aftermath of impacts, but were definitely not stable for the Hadean Earth. So that was kind of the big downside to surface environments now, is we don't have that natural production mechanism for prebiotic molecules. And then also it doesn't have as intuitive of a free energy gradient for life to get started on. So this is kind of like the two big environments people argue about. There's subsets like what kind of hydrothermal environment or what kind of surface environment, but we'll just ignore that for now. But when people are debating which of these environments life could have originated on, the debate primarily comes down to metabolism versus information first, or this energy versus information. So hydrothermal vents are really beneficial for energy first theories of the origin of life. So you need to set up some form of metabolism that life could easily take advantage of without having a lot of evolutionary mechanisms already in place. Hydrothermal events are nice because you have this hot alkaline fluid being pumped into a cool acidic ocean. We're assuming the ocean is acidic because CO2 would be a major constituent of the atmosphere. And that gives you a nice redox gradient between CO2 and hydrogen. Also, you're outgassing a lot of methane and hydrogen into the water. So it's been really beneficial for setting up what could have been a primitive metabolism. The downside to hydrothermal environments is the stability of prebiotic molecules. So end all be all goal, we want to be producing these nucleobases, potentially to produce RNA. There's some strong recent papers in the last decade arguing that maybe RNA was the precursor to all life, not only because it can store genetic information like DNA can, it can also act as a protein. So it can actually act to fold and carry out actions within a protocell. So if you could, single strand string together enough nucleotides to produce these short RNA strands that can then reproduce, you have, kind of the starter for the origin of life. RNA has a very short lifetime in hot environments, on the order of minutes. So it might be hard for them to oligomerize to long enough chains. Conversely, surface theories on the origin of life, you can have much cooler environments. So they can be much more stable for these prebiotic molecules. But then you run into this problem of how do you produce them? Now that we don't have a heavily reduced atmosphere for the Hadean, what mechanisms can we, rely on to, create large enough fluxes of these molecules being deposited into aqueous environments? So with that, I'm going to move on to what space weather is, because what we're arguing in this work is that an active young sun may have acted as a catalyst to produce a lot of these prebiotic molecules and deposit them into the surface environment. So space weather, what do I mean by it? Well, I mean these large SEP events, so solar energetic particles, where we get large fluxes of them being, extruded from the sun and then bombarding our atmosphere. So this is a solar flare from our own sun in 2014. These events occurring today are not only less frequent than we think they would have been in the past, but also lower energy. The reason for that is primarily just because the sun is spinning slower than it was 3 to 4 billion years ago. And as you spin it up, you get more magnetically violent events. You get more of these flare events, which are associated with SEP events. So as you can see, you have these SEP events associated with solar flares. Those particles are accelerated by coronal mass ejections along magnetic field lines, where they then will interact with the planets in orbit. So this is a nice little video of one of these events. This is, the Earth at different points in its orbit and how it's going to be coming into contact with that planet. So how often do these occur? Well, Kay et al. Did a paper where they estimate that you could have about 200 of these events per year. About a third of them will come into contact with the Earth's orbit, and the lifetime of these events will be several days. So as a first step in this project, what we're going to do is assume this is steady state. So assume that you just have a constant flux of these particles entering the atmosphere, and then how does it evolve your atmosphere over time? A more advanced follow-up study would be looking at time dependence of these events. So if you have maybe 6 hours occurring between each of these events, how does that impact how the atmosphere returns back? How much does it return back to its steady state before the next wave? And you build up particles that way. So how are we actually doing this project? So we have Vlad's who actually in the call runs magnetohydrodynamic model to determine the fluence of these SEPs. And then what we want to know is once they come into contact with the Earth's atmosphere, they shear open the magnetic field, you get some of these penetrating into the atmosphere. How far do they penetrate down, and what are they doing to the neutral atmosphere as they propagate downward? And they're going to be ionizing the neutral atmosphere. They're going to be dissociating it. So that's essentially what they're doing. They're just breaking things. They're destructive. And then what I've been doing is we then take these ionization dissociation profiles from the SEP propagation, and we run them through a photochemical model to determine what actually occurs to the atmosphere when you are doing these large scale changes on it. And then we feed that atmosphere back to the propagation code, and we just keep iterating until we don't get any more change between the two models. And then the final product we care about for this project is how does this impact the flux of prebiotic molecules into the surface environment? And I'll go through what some of those prebiotic molecules are, why we care about them, and then how many we're actually getting compared to other sources. Okay. So step one was calculating this SEP spectrum. This green line, this is what we're actually currently using in the paper. And what we really care about is we care about these particles that are about, larger than about 1 giga electron volts, because these particles have high enough energy that they're able to penetrate all the way down into the troposphere. And once you're creating a lot of these molecules in the troposphere, it's very easy for you to rain them out or to deposit them onto the surface. So previously, if you have maybe say like this blue line, you don't have very many of these particles penetrating down into the troposphere. Maybe they're stopping distances all the way up at like 80 kilometers. Then you're relying on molecular diffusion to transport them down low enough that you can then have more convective processes move them, and it's not nearly as efficient. So we want to get as many of these particles as low into the atmosphere as possible. So this is the fluent spectrum we're currently using. This plot's a little messy. Sorry, I should have made a clean one for this presentation. But just to give you an idea, this is what it looks like for, this is how many neutral species we're producing in the atmosphere because of these SEPs. So for example, this gray line, this is N-doublet-D in ground state nitrogen. What I mean by saying we're producing these is we're splitting N2, and I'll get to that in a second. That's like the real important chemistry that's driving all this. It's splitting that N2 molecule. And then we added ion chemistry to the photochem model. So we're also tracking how much we're ionizing the atmosphere and what that ends up doing to our final answer. So kind of the starting atmosphere we're using 0.6 gigayears. So we're looking right at that Hadean-Archean boundary, just to play it safe. We're not going earlier. We know there's life later. And we're using an 80% nitrogen, 20% CO2 to start, and 1 bar. We're also going to be doing a half bar case because there is evidence that the early Earth had a thinner atmosphere that it later filled out through outgassing. Okay, so I mentioned kind of the important kicker to all of this chemistry is that it's splitting N2. Life needs fixed nitrogen. So pretty much every prebiotic molecule is going to have atomic nitrogen in it. Modern life today has mechanisms for splitting nitrogen out of the air. But what we're looking for is we need some abiotic process to split nitrogen to give these precursor molecules that life needs. So, in the modern atmosphere, pretty much one of the only abiotic processes that's splitting nitrogen in the troposphere is lightning. So lightning splits nitrogen. And that was kind of the motivation behind the Miller-Urey spark discharge experiments. We would have lightning on the surface of the Earth. How much of this, nitrogen can we fix? So our new process is we now have these SEPs that have high enough energy to also be splitting nitrogen in the lower atmosphere. They're also ionizing N2 as they come down. And N2, when it recombines with an electron, we get a recombinative dissociation. So we also are dissociating it by ionizing it. That has a high enough energy threshold to do that. So since we care about mainly splitting nitrogen, but we care about all the chemistry, this is a little cartoony graphic of the photochem model I've been working with this year. Yeah, some of the physics in it. So we're tracking the photolysis, destruction of everything in our atmosphere. So we're looking at the sun at 0.6 gigayears. So we have much higher XUV flux. So photolysis, pretty much every species is just amplified. We also have convective processes in the lower atmosphere, which we model just using eddy diffusion profiles. At the moment, we're just using modern Earth eddy diffusion profiles, but we can always change those later. However, our results are pretty robust against how we're parameterizing the convective transport scheme, and I'll discuss that. I've actually removed this since I made the slide, but we also have a version of the model that does this high hydrocarbon chemistry that does impact, shielding, by this higher XUV flux. But since we're doing the Hadean atmosphere, which was likely very methane poor, we wouldn't have much of these hazes. And then also one of the big things I've added is all the ion chemistry to the model, because it didn't have that previously. And that's one of the big things these SEPs do is they ionize the atmosphere as they penetrate downward. Okay, so you have a large flux of all these particles into the atmosphere. They're splitting nitrogen, and their end goal, they're producing molecules. So you're catalyzing a lot of chemistry when you're breaking that triple bond. We're also breaking some CO2 also. So what are some of the potential prebiotic molecules that we're producing that we care about for the origin of life? So the first one's not a prebiotic molecule, but it's kind of a throwback to Vlad's original 2016 paper. It was kind of the thesis of that paper was, you could produce N2O. N2O is a greenhouse gas, and if you could produce enough of it, you could potentially impact greenhouse warming of the early Earth. So we, ran these calculations. N2O also photolyzes very quickly. So if you take into account its photolysis rate and its production rate, how much do you end up getting? Ignore the kink in the graph. My runs don't have that anymore. That's fixed. But we end up getting about, 4 to 6 parts per million of N2O using this SEP spectra. So it's not a lot, but, it's enough that you could get some warming out of it. I think Michael Way at NASA GISS has done GCM calculations looking at how much warming you could get for different N2O calculations. So, comparing this to his runs would be useful. And then whenever get around to actually writing this paper, I'll probably also just put in the N2O cross sections, into our 1D radiative convective model, just to also say, you get X Kelvin of warming for this atmosphere. Okay. So the second one is hydrogen cyanide. Hydrogen cyanide's kind of always been this golden molecule for the origin of life. Reason for this is it's probably the most important precursor molecule to forming adenine. HCN also in solution hydrolyzes to formamide. That's its main product. Formamide is important both as a solvent and a reagent in a lot of prebiotic chemistry. And as you can see, we're getting, well, this says 7 orders of magnitude higher when we include space weather. I'll compare that to other work and then explain why we get so much more. So these gray lines are from other papers. So their fluxes of HCN into the aqueous environment. And then what we did is we calculated what would that mean for the molarity in solution. So what's the actual concentration you build up to? And this is from Miyakawa et al. And it's assuming that the main loss process for HCN is hydrolysis, which it is in most cases. As you can see, this is comparing, I think it's to Zonley and Tien's paper, Tien 2011, where they calculated different HCN production rates. And the way they produced HCN wasn't from splitting nitrogen with space weather, but they assumed that, you'd be splitting nitrogen in the upper atmosphere, at least just from in the ionosphere. And you would have a flux of this atomic nitrogen down into the atmosphere. So this is the upper and lower range, assuming their production rates of that, of HCN, assuming that flux of nitrogen from the upper boundary layer, which I think in their model was either 80 or 100 kilometers. And that's why their paper, it was very dependent on how they parameterized mixing in their atmosphere, because you needed to transport that down into the lower atmosphere where you were photolyzing, methane. And then the byproducts of photolyzing methane with that atomic nitrogen gives you HCN. So they found they were limited by the amount of nitrogen they could transport down. We are limited, we're the green bars here, we're limited just by the amount of methane we have in the atmosphere. So we have a different limiter because we're using prebiotic fluxes of methane just from like serpentinization, et cetera. So, we fall right in the middle of their range. However, it should be noted that at their very low boundary, I didn't write down the number, that's unfortunate. At the very bottom of their boundary, they're using about an order of magnitude more methane to CO2 ratio than we are. And that methane to CO2 ratio is our limiting factor. So what I need to do next is create a plot of these just matching their CH4 to CO2 ratio so we can do a more direct comparison. But we find that we're in the middle of their range, but these top of their boundary, this is a 30% ratio. So 30% methane to CO2. So incredibly hazy atmospheres, which is very unrealistic for the Hadean because we don't have life at that point, unless, again, it's in the wake of a giant impact. And I guess just as a side note, because I'll show a plot like this again. Ocean, this is one Earth ocean. So this is just kind of the ambient concentration. And this is in a pond, and I forget the name of the pond, but it's in Antarctica. And it's kind of the minimum threshold for like, a volume of water that's going to be around year long that we think you could build up concentrations of this stuff up in. Okay. I skipped ammonia because it ended up, I should have removed the point, but it ended up not being as interesting as the other molecules. But the other thing you're producing is a lot of Nox species. And, you could just do the stoichiometry in your head. You're producing a lot of atomic nitrogen. So you're splitting N2. You're also splitting CO2. So you're going to end up getting these NO species building up in your atmosphere. Sorry, I don't know if you can hear that. I guess my neighbors are doing construction. We have all these Nox species, and you're going to be raining out most of that Nox species as HNO. So Sukrit Ranjan did a really great paper last year looking at, say you have a dump of Nox species into an aqueous environment, how much of that disproportionates into nitrate and nitrite. And nitrate and nitrite are really important molecules for origin of life. They're high potential electron acceptors. So they're acting in the oxidation of like methane and maybe hydrogenated CO2. And they're also in a lot of these intermediary reactions for the origin of life. They help in the replication of oligonucleotides. And in his paper, he set a threshold of about a part per million as this tentative lower boundary where prebiotic chemists said they would be interested if you could produce Nox or nitrate and nitrite above that. And as you can see, we get about a little less than 3 orders of magnitude increase. And we produce a lot of nitrate and nitrite in low volume reservoirs. And these upper and lower boundaries, they depend on the temperature you're assuming, as well as the iron content in the water. So we're using both the lower and upper boundary. His overall conclusion from his paper was you're probably not originating life in ocean environments if you rely on nitrate and nitrite, but these pond environments are really favorable if you don't have too much iron dissolved in the water. So we end up with a similar conclusion. You don't get that much in the ocean environment, but we get rid of that dependence on iron content. It really doesn't matter now, just because we're producing so much more Nox species being deposited into the reservoir. So that's really exciting. And I think in their paper, they're producing Nox from lightning. We're also producing it from lightning, but we're just outpacing lightning production by like an order of magnitude using space weather. And these numbers are even more dramatic for lower PN2 to PCO2 ratios. I mean, reason for that is you're just dissociating N2 even lower. And like I said, we're going to do a half bar case next. So we'll see these numbers just go up. Okay. Next molecule, this is formaldehyde. Formaldehyde is one of those other gold molecules in the origin of life. You have the foremost reaction, which gives you ribose. And it gives you a bunch of other more useless sugars, but it also gives you ribose, which is important in creating these nucleobases. It's also an important precursor molecule for glycine. And if you have enough peroxide in solution, which our Hadean atmosphere isn't that reduced, so we do have a decent amount of peroxide being rained out, formaldehyde and peroxide give you formate. And formates is one of the most used metabolic molecules for methanogens, which we don't know if it was maybe the first form of life, but it was at least one of the earliest, given how we think the Archean looked. So it's potential that you could be producing all this for the origin of life, but as a byproduct, you could be producing high quantities of formate in solution, which life then evolved to take advantage of. And again, that's highly speculative, but it's interesting that this isn't just important for producing prebiotic molecules. It could be setting up some of the early metabolisms. And as you can see, we get a ton of formaldehyde, and I'll talk, the next slide will explain why we get so much formaldehyde. And it's because we get a lot of CO. So just like we're splitting nitrogen, we're also splitting a lot of CO2. We get these large production rates of CO. CO's really, it's only removed. It only has like 2 removal processes from the atmosphere. One is surface deposition, and that's going to be limited in a prebiotic setting, and also hydrolysis of water. So OH radicals will scrub CO out of the atmosphere, and that's limited You're going to photolyze a certain amount of water vapor and not anymore. And CO is interesting because it's also been speculated to be a really primitive metabolism via this water shift gas reaction. So just CO and water goes to H2 and CO2. It's very small energetically, but for the quantities we're getting, promising. So as you can see, this is before space weather. CO's very small in our atmosphere, and then we're approaching this threshold called CO runaway, which is funny for people that do climate, CO2 runaway, but CO runaway, and it's where you're not able to adequately remove CO from the atmosphere because you've kind of already maxed out your two sinks. And as you can see, we're up at like 2% CO. So we're actually very close to that threshold where CO runs away and becomes a major constituent of the atmosphere. So just using this 2% atmospheric composition, we can calculate, the Gibbs free energy gradient from that water shift gas reaction, just assuming the atmospheric quantities. And we see that you get about 35 kilojoules per mole of energy from this reaction, which is ironically, I think 35.6 is the amount of energy you need to produce ATP, like the minimum amount. So, I mean, that's hand wavy, just saying, oh, we happen to magically match it. But it is interesting that this reaction is really low energy, but we can produce concentrations abiotically just using space weather that give us just enough energy to produce ATP, which is kind of that minimum amount you need for it to be interesting from a metabolic standpoint. All right, and then I'm just going to show you the final results and then sum everything up. And then we can go to questions because that's more interesting than me talking. And I forgot to replace my plot slide. You'll notice my plot does have these kinks in it. It does not anymore. Like I mentioned earlier, I iterate with the high energy propagation code and the photochemical code. And the more I iterate, the smoother these lines get. And they're much smoother now after like 8 iterations. But what's really important down here are these fluxes. So you'll see Nox species, we're up 3 orders of magnitude. Formaldehyde, we're up, less than between 4 to 5 orders of magnitude. And, HCN, we're up quite a bit. The reason we have so much formaldehyde raining out again is because we are right at that CO runaway threshold. And CO, when it's removed from the atmosphere with OH radicals, it goes to formaldehyde. Eventually it goes to HCO, and HCO goes to formaldehyde, and then it rains out because the formaldehyde's very, very soluble. So that's kind of the general conclusion of this paper, is just that we have this new mechanism, space weather. I'll stop sharing so I can address people. So we have this new mechanism, space weather. It's very efficient at splitting nitrogen down in the lower atmosphere. You're producing all of these prebiotic molecules that we're raining out into the aqueous environment. We're also potentially setting up really easily graspable free energy gradients. And all it relies on is that the young sun was more active. And I think since this is an exoplanet group, this is an interesting question. A lot of the time when we talk about really active young planetary systems, we worry about how it hurts habitability. And that's a valid question. I mean, you could be losing your atmosphere in short amount of time. You're affecting the stability of the atmosphere. But kind of the flip side of this is we could be setting up the necessary conditions for surface origin of life, which is really promising. So I think doing both of these kinds of work in tandem are important, so we can reality check ourselves, like, oh, if I keep cranking up the SEP fluence, I can be producing more of these molecules, but then the escape people can be like, yeah, but now your atmosphere is not stable. So I think when we look at exoplanetary systems, I think we should be excited by these really active systems, and this is a case for it. I think we could be talking about a mechanism which is generalizable for the origin of life, and it's just having a young planet around a young star, which is, I think, promising. And I'll end my talk there and take questions. I'm sorry if it was a bit short. But...
No, that was great, Ben. Thank you so much. Yeah, so if anyone wants to go ahead and raise their hand if you have a question for Ben, or you can also post it in the chat. And while folks are doing that, I was just curious, Ben, I'm not an expert in this at all, but going back to that figure you showed with the CO, What are the two major sinks there? I have not heard of the CO Runaway. So I was just curious if you could just elaborate on that a little bit more. And then we'll go to Ravi after that.
Yeah, so CO runaway, people mainly talk about it in the aftermath of like impacts when you have huge fluxes of CO just from splitting CO2, or just impacts can deliver CO also to the surface. But CO's, its two mechanisms for removal is surface deposition. And Krecha et al. 2015, they have a really nice paper where they kind of calculate CO surface deposition as a function of aqueous chemistry. And if you have life that's utilizing this CO, that sink can be really fast. So on the modern Earth, CO has a very high deposition velocity. But in a prebiotic environment, it builds up in solution, and that gradient gets smaller and smaller, and that sink becomes less and less. So that's one of the main sinks. And then the other one is just being scrubbed out by OH in the atmosphere. And that's mainly just controlled by your photolysis rate of water. And that just has like a set limit. Like you're only going to photolyze so much water for an XUV spectrum. And then after that, if you're still producing CO, it just starts building up. So that's kind of the idea of CO runaways. You can hit this threshold where you've capped out your sinks, you're still producing it, and then it just becomes a major constituent very quickly.
Gotcha.
Yeah.
Very cool. Ravi, do you want to go ahead and ask yours?
Yeah, so two quick questions, Ben. It was wonderful talk, actually. Very good. So one question is, did you simulate any of these events or the resulting molecular species with repeated time-varying events of this energetic particle flux? And how does that affect the prebiotic chemistry or the origin of life question? Because it's not just one-time event, right? It happens over billions of years. The second question is, do you have any spectral features either in the transit spectra or emission spectra of how detectable are these molecules that you are talking about?
Yes. So, okay. So in this paper, no, this is time insensitive. So what I've been assuming is, I think it was K et al. 2019, but they assume that there's 200 of these events that impact the Earth. Wait, maybe it was 200 events a year and a third of them impact. Hang on, let me double check. Yeah, 200 events per year. A third of these impact the Earth, and then the lifetime of these events are several days long. So it comes out to be, roughly steady state, which is what I've been assuming in this paper, that you just, roughly have a steady state given how active the sun was at that period. But I do think a next follow-up study to this would be to do time sensitive, because maybe you, like I mentioned, maybe you have like a 6 to 12 hour window where you don't have these particles coming in. How does the atmosphere then decay back to it? How far does it decay back to its neutral state between each thing? And maybe you don't build up very much, or maybe you just keep building up more and more because it doesn't have any chance to decay back to it. So that'd be a follow-up study, not in this one. And then your next question.
The second question was about the spectra.
Yeah. So I've thought about this. Me and Sukrit Ranjan, I think it's a paper we want to do whenever I finish this paper. But out of the minor molecules, I guess I'm just not very optimistic about detecting anything with next missions in the IR. But I think CO potentially. So CO does have 2 absorption features in the near IR, or no, one in the near IR and one in the IR that are decently strong. And if this process does produce CO-rich atmospheres where you have CO as like several % of the atmosphere, I think that might be promising. Looking at planets around stars that we know are active and looking at, is CO a detectable feature, which otherwise, wouldn't be if it was just around a sun-like quiet star. So I think that maybe that's a promising molecule to look for. And I think it's something I want to do eventually. Like maybe ground-based telescopes or something like that. Yeah, thanks. Those are good questions.
Great. And Peter, do you want to ask yours?
Sure, thanks. That was a nice talk, Ben. My question is, can you comment on whether and how the planetary magnetic field influences this effect, like do the field lines help get these particles deeper into the atmosphere? And if you didn't have a magnetic field, would these photolysis rates go down?
That's a good question. And it's probably a better question for Vlad, since he's doing the part of the modeling that calculates how the magnetic field of the planet impacts it. But to my understanding, is because these events are so energetic, you're actually you're shearing the magnetic field line all the way down to like, mid latitudes. So even with like an Earth, I think we're simulating this with an Earth-like magnetic field currently, and this is how much we're actually getting into the atmosphere. I don't actually know if it's if it's delivering more particles into the atmosphere. To my understanding, it actually acts more as a shield than as a deliverer of these particles. But since we're shearing it open to mid latitudes, we're getting a lot into the northern, like the high latitude of the planet. A lot of these particles, large fluxes of them.
Um,
Yeah,
great talk, Ben. So yeah, I just want to comment on Peter. Hi, Peter. To your question. So basically, when we talk about space weather, we normally not only talk about SEP events. We talk about the, I call it Trinity. It's three events that are come together and in association. It's a flare, okay, that gives you XEV particles, and basically those XEV particles can produce also those molecules in the upper atmosphere Ben was talking about. It's according to Tian's paper. And then, flares come with the coronal mass ejections, and with the ejections of those, bubbles, of bubbles of magnetized plasma propagating out and then colliding with the Earth magnetosphere. And as they collide with the Earth magnetosphere, they compress it and open up the polar cap. So the polar cap, as it is today, normal around Alaska, they go down all the way to like 30 degrees latitude. That's what, we've calculated back to 2016. And that opens up the big reservoir, the big cross section for the particles to penetrate in, for that space. And that was calculated for the current magnetic moment of Earth. So if the magnetic moment of Earth is lower, that means that at the same dynamic pressure of your coronal mass ejection, you compress it further and you open up all the way to like, to around like equatorial regions. So that basically the point of it. That, yeah. And the third factor, that as those CMEs, they propagate out, as Ben was saying, they ignite shock waves, and those shock waves generate energetic particles that were calculated from the SAP model, within the physics-based model. So those three events, they come together. So that's why the flares, they induce extreme UV emission in the upper atmosphere. SAPs, they open up the magnetic field so that the particles can penetrate in and produce SAPs the same way.
So which of these actually contributes to the chemical photolysis that Ben's modeling?
Like it's SAPs.
Or is it the particles?
SAPs. Yeah, but I would just say that that Ben was talking about SAP events. Yeah, the solar particles that go penetrate into the lower atmosphere. But the one event that needs to be looked together, so that the upper atmosphere production of HCN that and other molecules that was discussed in Tian's paper is the part of the same thing. Because I say that if you have SCPs, you do have XUV particles. Okay, so XUV photons that will produce that additional flux of HCN. So we basically just comparing it just for the sake of the seeing that what is the competing factors we have and production mechanisms, up there and low there. So at different layers. Yeah.
Thank you.
Thanks.
I see some of the questions in the chat. Is it okay if I just read
Yeah,
them?
yeah, I definitely go ahead. I think Wejo was asking a similar question about the magnetic field.
Yeah. Yeah, for Wage's question, Earth-like right now. So just modern Earth magnetic field. Then Max, remind us again how these pathways depend on the oxidation state of the atmosphere. That is, many scenarios that form prebiotic molecules require reducing atmosphere. Perhaps one of the advantages of your high energy mechanism is that you can break into and make molecules in an atmosphere that is not reducing. Yeah. So the way it depends on it is, I forget the name of the paper, but there's really, I really should remember all these authors, but there's a really nice paper that looks at the C to O ratio of your atmosphere. And then it looks at how much Nox species versus HCN you're producing. And there is kind of this like threshold, I think it's at like 0.5 for that C to O ratio. And it is true. So like our atmosphere is relatively oxidized, and, relatively, we have 20% CO2. So we're producing a lot more Nox species than we are hydrogen cyanide. And like I mentioned earlier, HCN, which is, that's really dependent on a reduced atmosphere. we're limited by the amount of methane we put in our atmosphere. So we're using really low concentrations. I mean, we're less than part per million, because we're assuming it's all from serpentinization. But if you did go up to more reduced atmospheres, you would produce more of the hydrogen cyanide. And I do think one of the advantages of this mechanism is we're able to essentially get the most out of that oxidized atmosphere as we can, that we otherwise weren't able to previously, because we relied on doing this all in the upper atmosphere and transporting it downward. So that's a good question.
That was paper, Ben, that was paper by Paul Rimmer,
Yes.
2019.
Oh, thank you, Paul Rimmer.
Right. And I think Richard was asking about why the ponds have higher concentrations. If you could give a little bit more explanation on that.
Yeah, that just has to do, it's so if you, there's two papers you could look at. There's Sucre Ranjan's paper, and then there's also this Miyakawa et al. 2002. And they calculate steady state concentrations as a function of flux into the reservoir. And it's just directly proportional to volume of that reservoir. So if you have a higher volume reservoir, it's just going to make it more diffuse. So for the same flux. So if you can have a smaller reservoir, you build up higher concentrations in the same amount of time. Have you all looked at sulfur chemistry at all? That's a good question, Cleves. No, I haven't. We have really basic sulfur chemistry in the photochem model. A lot of it's just remnants from Sonny Harmon's sulfur MIF paper. So we have some of the basic chemistry in the model, but nothing beyond like HSO4 and like just some of the really basic ones. We're not producing anything of higher complexity. Yeah, I mean, that's a good question.
Great. Does anyone else have any other questions for Ben?
Yeah, actually I do. Hello.
Hey, Estelle.
I had a question. So if we want to extrapolate this work for exoplanets, what would be the primary conditions of extrapolation? As in how specific to Earth was it? Is it just about the species that are in the atmosphere, or are there other conditions that we should be aware of?
Yeah, so this, I think what's really nice about this is it is really generalizable, and there's just two factors you really have to take into account. One is going to be, what is that SEP fluence? So, I mean, this is for a sun-like star at 0.6 gigayears. How different is that going to be for, an M dwarf or, et cetera? So, I mean, that's something you'd have to model, because that would be different. And then the second one is just, what does your neutral atmosphere look like? And I feel like, 1 bar, 20%, it sounds Earth-centric, but I mean, it's pretty generalizable. But like, what if you did have a more reduced planet? So like, let's say we had like a Mars-like exoplanet at the same period, and we had maybe a lot more CO to CO2 and a lot more methane. We actually find in those very reduced atmospheres, it's just better for us because we're limited by the amount of reduced species that we're able to break apart. And if you had an exoplanet that was, not just mildly reduced, but heavily reduced, everything in this paper would be amplified except the Nox species. Then you'd be producing less Nox species, because that's more on the oxidized end of the spectrum. But you'd be producing more formaldehyde, HCN, et cetera, which I think is probably more exciting prebiotically, but I'm also not a chemist, so I shouldn't speak to that. Yeah.
Excuse me. Yeah, I also want to comment to Estelle's question. Another factor, that's all great factors that Ben mentioned, but another factor that wasn't mentioned is the atmospheric pressure. So the point is that if we are looking at an exoplanet around even more active star like our sun, like M dwarfs, let's say, right? So then the XEV fluxes will erode the atmosphere, and so we would expect much lower atmospheric pressure, might be at the level of, let's say, fraction of a bar, let's say like a quarter of a bar, half a bar to a quarter of a bar. What does it do? So the lower the atmospheric pressure, so the lower the column density, so that much less energy particles go to that level of the low atmosphere, okay? Producing those compounds, that molecules that Ben was talking about. So that means that you can increase the production rate and the concentration in a lower atmosphere only because you have much more particles reaching that level that can then react, producing the atomic nitrogen and all follow-up molecules.
Yeah, it should be noted though that so lower atmospheres, you'll get more of these particles lower into the atmosphere, producing prebiotic molecules. But like I mentioned, we're close to CO runaway, so we're splitting a lot of our CO2 in the atmosphere. And as you can notice, the upper altitudes, it falls off very sharply when previously it was well mixed. Part of the reason it's stable in my model is I'm doing an inverse calculation where I fix the surface mixing ratio of CO2, and I just tell the planet, pump out as much CO2 as you can to maintain that surface mixing ratio. The thinner my atmosphere is, the further down I'm going to be dissociating CO2, and the more unrealistic that assumption might be, because I might be like pumping a ludicrous amount of CO2 in to maintain a, say, 20% mixing ratio. And in this model, I just did that because we needed, we have climate constraints. I can't have a snowball for the origin of life. So I fixed it at 20%, but yeah, I don't know, just a side thought.
But it also depends on the level of volcanic activity, right? If your planet is more volcanically active, you can produce more CO2, basically, even though you photolyze some of it.
Yeah, that's true.
Great. So we have some time for a few other questions. Anyone else have any other questions for Ben?
I'll type my email.
Oh, cool.
That's to you. Sorry. I can do it to everyone.
Oh, yeah, no, you're fine.
That's my email if you have questions too.
All right. Well, if no one else has any other questions, I want to thank Ben again for coming and talking with us today. I think that was a great discussion.
Yeah, thanks for having me.
All right. Well, I hope everyone has a great day. And thanks a lot, Ben.